Just a quick review of what we went through with 1-3 yesterday. We talked about how to find domain and range from a graph. We talked about how to evaluate a function based on a graph, right, where I give you the x, you give me the y. We talked about increasing, decreasing behavior, which means also constant. The word constant is not usually in the instructions, but that's obviously part of it. We talked about max and min, and we talked about, what am I missing? The zeros of the function. Okay, so that's kind of where we left off. We graphed this function yesterday, and we said we were going to find the relative max or min on the graphing calculator. So when you graph it using, like a TI 84, 83, whatever you've got, if you want to practice this, this is one of the ways that you can find the exact max. So when you type in you're going to go to y equals, right? You're going to type in your function here. You're going to hit graph. And then, I'm going to show you based on a picture. Hang on.
Because I'm going to hit record.
Okay, so I graph the function, right? I hit the y equals, I entered in the function, and then I hit graph. And then there's a button that says calc above your trace button. If you hit second trace, you get this calc menu. If you hit 4, so we're trying to find the max. I hit 4 to find the maximum. The first question is going to ask me is your left bound. So you want to get as close to what looks like your maximum as you can, but you want to be on the left side of the maximum. So I'm going to scroll my arrows over a little bit to the left. I'm kind of close to where that maximum is, but it's not exact. I'm setting up my left bound. So I'm asking it to find where the max is, but you got to give it a range, okay? So I'm going to click enter. It gives that little line. So we're saying, okay, that's going to be left of the maximum. Then it's asking me for the right bound. So I scroll my little trace to the right till I'm past the max, and I hit enter. And now that's my right bound. And then it says guess, and I just hit enter, and it brings me exactly to my max. So that's going to be your accurate max. Same thing will happen for a minimum, okay? You'll hit minimum, you'll do your left bound, you'll do your right bound, and then you'll hit enter on guess, and it will bring you to your exact max or min. Everybody saw that? Everybody practice it that has their calculator? Ask for it. It doesn't ask for it, but let's talk about increasing and decreasing behavior on this function, and then also let's talk about domain and range. So if I look at the function here, so I'm just going to pull this one in so that we've got a good image of it. Okay, if I asked you for increasing and decreasing behavior, remember you start left to right. So the first kind of pattern I have looks like that, right? The first path until it changes directions. And what kind of behavior is that? Increasing. And remember you give your x values. So my increasing, this implies it's getting cut off, which means it's increasing from negative infinity up to the x that is here, which is negative 2.25. Monica.
How do you know it's negative 2.25?
So that will be based on your max and your min. Like everywhere there's a relative max or min is where your point is going to change direction. Does that make sense? From a graph, so you're going to see this type of question in two ways on your test. One, I'm going to give you a graph. The point should be obvious. You could tell me the change in direction. The other is you're going to graph using your graphing calculator. You're going to want to find those points in which they change direction by either using the trace or the max and the min, and then that's where they would change. Does that make sense? Okay, now can a point be increasing or decreasing? If I put a dot on my graph, is that point increasing or decreasing? No, okay? A point itself cannot be increasing or decreasing, which means these are always going to get parentheses on increasing and decreasing. The only behavior a point can take on is constant. So if my graph starts constant, meaning, like ignore what's in the background there, meaning I have something that looks like this, right, where it would start at a dot, then that's a bad excuse because that's not a really straight line. Let's say that's a straight line, okay? That would start constant. I'd get a bracket on that number, okay? Or it ends constant, meaning that maybe my graph looks like this, and then it stops, and then it drops, and then it goes to the right. Well, that wouldn't be a function, but it ends. Let's do that. So it goes up, maybe it comes down, maybe it turns, and then it stops constant. That way you would get a bracket all the way on the right. So we'll do a couple examples like that, but those are the only times you're ever going to see a bracket on a number when you're talking about increasing and decreasing behavior, is if it starts or stops constant. This point in here technically is shared by the constant part and the decreasing part, so that would get a parentheses, okay? So let's go back. now that we've got that gets a parentheses. And then the behavior changes, right? And it starts falling, which means it is what? Decreasing. And it decreases from negative 2.25 to what? Positive infinity. So it's going from left to right, okay, when we're talking about the values that go into that interval notation. How about domain and range? What's the domain on this function? All real numbers. Negative infinity to positive infinity. My arrows are going to point left and right. What's the range on this function? What's the lowest point on my graph? Negative infinity. What's the highest point on my graph? 10.125. And bracket or parentheses on the 10. Bracket, because we include that point. It's part of the graph. Monica.
Did we find the mean?
There is no min. So because it's going to keep going and not go down and come back up, there's no relative min on this one. So you can have more than one. You can have none. Okay. Every time it goes up and comes back down, you've got a max. Every time it goes down and comes back up, you've got a minimum.
Why is it a main negative infinity?
Why is what?
The domain, the all real numbers.
Because the domain, remember, think left to right. Those arrows, while they look like they're pointing down, they're actually pointing down and out, right? So the further that, this purple side, right, the further this goes as it continues down, 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 it's also going left, 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 left. Does that make sense? So it will go to negative infinity. And then the same thing for the blue. It points down, but it points to the right, which is your domain. Maria.
The function was flipped upside down. Would you just call it the minimum then?
Correct. So if the function was flipped so that it points up, you'd have a minimum only. And your domain would be the same, but your range would change to be the y of that minimum to positive infinity. Yep.
How do you know it's exactly 10.125?
That's what you use your calculator for. So your calculator is going to let you find that exact point, and then you'll use that point to establish your ranges. So once I know that this point here, right, was, I mean, we use this is on the graphing calculator from the app, but that your graphing calculator should do the same thing. That point is negative 2.25 and 10.125. So that's the y coordinate of when it changes. All right, so I'm actually going to show you 2 ways to graph, and you decide what you want to do, okay? With the lines, it's kind of easy to interchange. Once we get into things that are a little bit more complicated, I would probably stick to method 2, okay? But just watch and figure out what makes sense for the lines. So to graph a piecewise function, which means it's got parts. It could have 2 parts, it could have 3 parts, it could have 4 parts, okay? This one has 2. The first thing you can do is graph them as 2 separate functions. So I can graph this first. So I would say f of x equals 2x plus 3 is what kind of a shape? It's a line. F of x is really what letter? Y. So this is really saying graph y equals 2x plus 3. So I can start by graphing that. I'd go up to 3, plot a point, up 2 over 1, and connect my line. Then I can go graph the second one, which would be a y equals 3 minus x. Or y equals negative x plus 3 if it's in slope-intercept form. So I'd go again, positive 3. This time my slope is negative 1, so I'm going down 1 and right 1. And my graph would be something like that. With me so far? Okay, so think about what we learned yesterday about graphs of functions and the test we use to figure out if it's a function. If I left it the way that it is, what's wrong with this graph?
Horizontal line test.
Vertical line test. But yes, vertical line test is going to fail it, right? Yes, everybody see that? If you graph your piecewise function correctly, it is a piecewise function, which means it has to pass the vertical line test, okay? So if you go to graph it and you're turning it in and the vertical line would fail, then you know you did something wrong. So what we have to do now is apply the restrictions that were given to these. So the first one says that that purple line is only a line for where the values of x are less than 0. So I'm going to go back to my purple line. I'm going to find where x is 0, which is here. Less than would be everything to the left of it, which is going to point back down here. And I'm going to erase everything that's to the right of it. So in notability, you don't get like that erase, right? It's a strike through. So I'll just tell you, when I teach this in notability, I go back over it again a second time, and then I erase my original one. I don't know if that makes sense to you. Okay? But think about the fact that when you get a quiz or a test, you're not getting it on notability. So we're going to be erasing, okay, the lines. The purple one, not yet. Yeah, I mean the purple one, yeah, we want to erase everything to the that is bigger than 0 for the x. Now the blue one is greater than or equal to 0. So the blue one is true for the values that equal 0, which would be here, and everything greater than it, which is going to go to the right. And that means erase everything to the left of it. That is my piecewise function. Okay, that would now pass my vertical line test, right? There's no overlapping points. Questions so far? Okay, so the second way to graph these no. So the second way I would probably recommend for when we start to get a little bit more complicated on our graphs. These are both lines, relatively easy to graph, erase, that kind of thing, right? But when we start to get into parabolas or cubic functions or square root functions in which you don't have exact points as easy, then I'm going to recommend this method. So what I do here is just plot points, but I plug in points from the range that is assigned to the individual function. So for this one here, I'm doing the values that start at what they give me and then get less than that because it says less than 0. So for my x values for this first one, I'm going to start with the one they give me because I have to have a dot there. It's just going to be an open dot. So I'm going to start at 0, and then I want x to be less than 0, so I'm going to go -1 and -2. And then I just plug those in. So 2 times 0 is 0, plus 3 is 3. 2 times -1 is -2, plus 3 is 1. 2 times -2 is -4. Plus 3 is -1. And then I plot those points. So 0, 3, and it's an open dot there. -1, 1. -2, -1. And I know it's pointing left because it's less than 0. And then I do the same thing for the second one. But this time I'm starting at 0 and getting bigger than 0. So 1, 2. So 3 minus 0 is 3, 3 minus 1 is 2, and 3 minus 2 is 1. 0, 3, now it's a solid dot. 1, 2, 2, 1, and my graph goes that way. So again, with lines, probably, I mean, you take your pick. It's not that hard to do it either way. But you'll see when we get to the next one, you're going to eventually pull in here some parabolas, some square root functions, some cubic functions, things that you won't have exact points for.
So the dot on 0, 3, it turns like you shaded in?
It actually got filled. Yep. So if this was, let's say, so let me alter it so that you can see what would happen if it wasn't. Let's say that this was a 4 minus x. Then my graph would look like this, where I'd have an open dot on the blue one and a solid dot on the purple one. So as long as one of those is open, it still passes my vertical line test, right? Which means it's still a function. You can't have 2 solid dots on the same x. That's how you'll know you did something wrong, okay? All right, so let me show you how to do this on the graphic calculator because you can do piecewise functions on the graphic calculator. All right, so try it out and see how far you can get. Notice that this time there's a line and there's a parabola. Okay, so maybe the line you can do by your y equals mx plus b instead of plotting points, but maybe the parabola you want to plot points unless you know exactly what that looks like. So the first one I graphed like just the line, right? I just used y equals mx plus b. And then it says for the values in which x is less than or equal to -1. So I would go back to where x is equal to -1, which is here. Put a solid dot, less than or equal to is going to point left. And I would erase everything that's to the right of that line. Then I plotted points for the parabola, okay? So I did where x is -1 and then greater than -1. So I did -1, then 0, then 1. -1 is -1. So this would be a point here, and it's open because it's not or equal to. And then 0, -2, and 1, -1. I know it's a parabola, so my curve is going to eventually come back up. If you're unsure, you want to keep plotting points until you see what happens, okay? Isabel.
Why'd you plot -1 if it has to be greater?
Because you do need that dot, because think about it, the very next number is part of that graph, right? So -9.999999999 has to be on that graph. But you use the open dot to show it can include -1, but everything after it. So you always want to use these, if you're plugging in points, use those as your initial first points, and then either one to the right or left, depending on the range. Maria?
How do you solve this one without like plotting points just by looking at the...
You'd have to be pretty exact on your parabola. So, I mean, if you remember a parabola that is x squared minus 2 is a shifted down 2 places, which we're going to talk about more in the next section, right? So I could go down 2 places, plot my vertex, and then because there's nothing in front of the x squared, go up 1 and over 1, up 1 and over 1. So you can graph it that way. But you need at least those 3 points to establish the curve. So if it was like a cubic function and you don't know exactly what it looks like, or square root, then you're going to want to plug in points. And a piecewise function can be 2 parts. It could be 3 parts. I could add in here a horizontal line at the end, okay? It will start, stop, start, stop, start, stop. There's no limit to how many, okay? Maddie. All right, so you should have gotten something like this, okay? The yellow is the first line. You start at +1, go up 2 over 1, but erase everything that is greater than -1. That yellow dot would have been solid, so the graph for the purple should have been a solid dot. And then for the parabola, unless you know exact points, which we can do a shift, obviously, we're going to talk about in 1.4, like transformations of graphs. You can get a roundabout from your shift. You could know that that's a parabola that's shifted 2 places down. But you want the exact points to figure out where they overlap, so you need at least those 3 points. So I would have plotted the point at -1. That should have been an open dot. And then I got 0, -2, and 1, -1. And I know it's a parabola, so it's going to point up as it moves to the right.
When it says greater than -1, you can start at 0. You can put 0 after that.
Great, yeah, anything bigger, yeah. So you want to start at the one they give you. Just remember if it's supposed to be a solid dot or an open dot when you plot that point. But you have to include -1. Otherwise, there's that space in between 0 and 1, and that should be part of your graph, right?
But how can you include -1 when it's like...
You're putting an open dot on it, though, right?
Oh, because I use 0, 1.
But then you miss all these points in here, right? If you don't include, then you miss all that little, I mean, it's a little space this time, but you miss all those points in there, and those points are part of your graph.
I got it. I did it right.
Oh, you plugged in -1?
No, I didn't, but
Oh, you just like went up on your graph.
So the table that you did on the side is
Yeah.
for the
Parabola, yeah,
And those are the points that it has to touch on the line.
correct.
How many points do you want
So parabola, I would say 3. Line, 2. Anything other than a line, I would say 3. Questions on the piecewise function. So now you know how to evaluate them and how to graph them, right? Okay, even and odd functions. So there's 2 ways to test if a function is even and odd. The first is algebraically, which is what we're going to do now. The second is from the graph, okay? This says, and this is like the definition of it. I feel like half of my job is interpreting what math speak is into what a 17, 16, 15-year-old would understand, right? It says the function is even when for each x in the domain of f of negative x, equals f of x. What that means is if I take negative x and I plug it into the function, it goes back to the original function. Does that sound familiar? Yeah. What is that also a test for? Symmetry. What kind of symmetry? Y-axis. So if it is symmetric to the y-axis, the same test, then it is considered to be even. Okay? So y-axis symmetry. Same thing. And then the second one says a function is odd when for each x in the domain of f of negative 1 equals the negative f of x. This basically says that if I plug in a negative x and a negative y, it goes back to the original. What is that?
Wait, no.
Yeah, because this is negative x, this is negative y. So it's saying if I change the x, right, and you got to decipher math speak, right? If you plug in a negative x, then you would get out a negative y, okay? But all that means if I plug in a negative x and a negative y, it go back to the original, which is also the test for what?
Double symmetry.
Origin, okay? So if it's symmetric to the y, it's even. If it's origin, think origin, O, right? Origin and odd both start with O. Origin and odd. If it's symmetric to just the x-axis, then it's neither. Or if it's not symmetric at all, then it's neither. So it can be even, odd, or neither. And you literally just write neither.
How would you tell them to neither?
It would be neither one of those. So it's not symmetric to the origin and it's not symmetric to the y-axis. So on your homework, if you haven't started already, you'll see like there's a lot of them where you have to say like none. And it says write capital D, capital N, capital E. Okay, that's what your answer for none is. It says it in every instruction that says if it's none, put this. Just pay attention because I know you guys are getting like mini heart palpitations if you get them wrong, even though they're right. Right? Yeah. Well, all right, then from a graph, it's even if it's symmetric to the y-axis, which we just talked about. And if it's odd, then it's symmetric in respect to the origin. So the test is kind of different for algebraic. You don't have to change the x and the y. You just have to see if it changes the sign, but you could do it the same way. But from the graph, it's the same. So if a graph is symmetric to the y-axis, if it does this, this is going to be even, right? I could fold it right over. If it's symmetric to the origin, like this, then it's going to be odd. So I think of origin as like folding it along your diagonal or folding it down and over, I think is probably the easiest way to look at it. If I took that top part, folded it down, and then flipped it over to the left, then it would be symmetric to the origin. And that would be odd. There's by graphs, which is exactly what we talked about. A function is even if it's symmetric to the y-axis, so I fold it over the y-axis and it would be even. A function is odd if it's symmetric in respect to the origin. Origin is like over the y equals x line, but I basically picture origin if I can take the top part of my graph, fold it down, and then take the right part and fold it left. And if it overlaps, then that would be your origin. How I picture it, okay? But even y-axis, odd, origin. All right, last one. It says graph the function and determine if the function is even or odd, and which intervals, or the intervals for which f of x is greater than or equal to 0, and then use the graphing utility to verify. So I'm going to save us a little bit of time in the graphing, okay? But if you think about, and we're going to eventually get to this, okay? But if you think about what this shape is, so 1.4 is all about transformations. What kind of graph is this? If it's x squared? Parabola. If it's negative, it means it points down, and that 4 is my vertex, right? So I'm going to graph it, but you would have obviously been, you know how to plot the points. Okay? And then your intercepts are 2 and -2. So I'm just doing this to save us a little bit of time because the bell's about to ring. But this is what the graph would have looked like had we actually plugged in points. So question is it even, odd, or neither? Your answer is what? Is that symmetric to the y-axis?
It'd be even.
It's even, yes. Is it odd? No, because it can be both, right? Like a circle is going to be all of it, right? All right, so B says, find the intervals for which f of x is greater than or equal to 0. So translate that into normal speak for me. What is f of x? Y. Where is y greater than or equal to 0? Not just for this graph, but all graphs. Where do you look for where y is greater than or equal to 0? Quadrants 1 and 2, right? Everybody understand that? So this area here, from the x, because it's or equal to, from the x-axis and above is where y is greater than or equal to 0. Everybody understand that? So basically this is saying what part of the graph for what values of x is my graph on or above the y-axis. So what's the first point at which it hits the x-axis?
0.
The y0, what's the x?
2,
-2. Where's the last point it hits? +2. It's an or equals to, which means what goes on those numbers? Brackets. So the interval for which f of x is greater than or equal to 0 is the same thing as saying, where does this graph go, hit the x-axis or go above the x-axis? And you're giving it an interval notation in the x values, okay? So I start at -2, and then I go to +2. Eventually, these graphs are going to get jazzier. So like if this had gone down and come back up again, right, then I would also include from that point on, so it looks about 5. I would say it is from -2 to 2, union 5 to +infinity. Okay, so you can see that it happens on more than one interval. Does that make sense? That graph would no longer be symmetric to the y-axis, though.
I mean, how does the red happen?
The equation would change. So your equation could be like an x to the x cubed, where you've got other, like an x squared term and an x term, and it will start to snake it through. Yep.
If that like red thing was there,
Yep.
would there be a bracket on the 2?
There would be a bracket on which 2? Yeah, there's still a bracket there because it's greater than or equal to 0, right? The y is 0 there. And then it would also be 5 to +infinity like that if the red was there. But it would no longer be even. It would be neither, right?
So for this one,
I'll go real fast. So there's one other thing in the homework. It asks you have to like plug an equation in that has a y squared, right? Like y squared plus 3 equals x. And you have to plug that into your graphing calculator. I have to solve that for y, right? In order to plug it in the graphing calculator. So I would have to get y squared equals x minus 3, and then I would square root both sides. But what happens when you square root? Plus or minus. So when I type that into the graphing calculator, this is actually a question very similar. Is it?
Yeah.
Oh, good.
And then
So, but on the graphing calculator, it's not. You'd have to enter in the plus or minus.
Did I do that?